This presentation covers the final project that our team has created for Introduction to Feedback Controls. Our project group members were Colin, Hovden, and Trevor Reed. The problem we wanted to analyze was part of the flight system for an unmanned aerial vehicle. UAVs are becoming more and more popular with government agencies to remove surveillance personnel from the field and to be able to cover more and more territory with less people in the field. These UAVs are becoming more and more complex as technology progresses, but because of their remote control abilities and their many applications, new UAVs have to be able to be controlled by simple tasks on their own or through operator control. We want to simplify our analysis of the problem to variables that affect the flight path of UAVs. Our goal is to design a feedback control system that will allow for quick response in the altitude controls of the aircraft and will efficiently control the altitude changes for quick maneuvers by the aircraft. The two variables we would like to analyze using a feedback control system are the angle of inclination of the rear flap, alpha, and the pitch angle of the aircraft, theta. The input variable to our system is the change in flap angle, and as this change passes through our plant design, it will output to us the change in pitch angle of the aircraft itself. The figure above shows two angles and provided relationship between the two variables we are trying to solve for. Our plant design has solved for the transfer function that allows the control system to take the flap angle and output the pitch angle of the aircraft. The closed loop transfer function is when we took the feedback of our plant with a return side of 1. These two transfer functions will allow us to be able to analyze our problem system and to model and tune our setup to operate most efficiently. The transfer function for our problem unfortunately is unstable due to the pole on the imaginary axis. However, we were able to circumvent this issue by placing the controller into a system and closing the loop around the transfer function. By doing so, we have found that the closed loop transfer function is in fact BIBO stable as proven through the Routh-Horowitz analysis. The closed loop step response information is listed above. The next step of our problem analysis was to create and design our feedback control system. We used MATLAB and Simulink to aid us in the modeling of our feedback control system. By use of controller tuning function in Simulink, we were able to determine an appropriate controller for our desired system requirements. The PID controller we used for analysis is shown here. Our group used this controller information to finish creating the finalized block diagram of our design feedback control system. We included a disturbance in the system to account for a possible adverse interaction the aircraft might encounter during flight, such as high winds, aerial debris, or the launching of ammunition from the aircraft. All of these parameters are outside factors of the original designated control system but should be taken into account when creating a finalized design for the system itself. Now that our control system was defined, we needed to ensure that the system would be able to meet our system requirements. We wanted our system to have a rise time of less than 1 second, a settling time of less than 5 seconds, and a 0 steady state error. By having very small rise time, we are ensuring that our control system will have quick response to either the remote pilot's commands or the sensor of the onboard automated system. By having a reasonably small settling time, we know that our design will not overshoot the desired change in altitude by a large amount, thereby not wasting fuel or time. And finally, we want 0 steady state error to ensure that the control system will always converge on a real achievable value. This is because if there is any error, the plane will either fly downwards into the ground or upwards into space uncontrollably if the system returns a value that is 0 or infinity. The MATLAB step plot on the right and the following specifications show how we were able to prove that our design control system will meet these criteria. We were also able to determine that our design is a little robust because of the determined phase and gain margins. We are able to increase the gain of our controller and still have a stable system that will continue to meet our criteria. This is a very good quality to include with the control system so that changes in the system can be made without having to completely redesign the entire system. So in conclusion, the system that we wanted to control is an unmanned United States border control aircraft. The input for the system was the angle of the elevator flap alpha, and the output was the pitch angle of the aircraft, theta. To control the flap angle, a PID controller was used in conjunction with a predetermined transfer function that related the two variables. Upon deciding on the controller type, the constraints were taken into account so it would meet the design specifications of rise time, settling time, and steady state error. Despite our minimal experience designing control systems, our group is satisfied with the controller we have designed and believe it could work in reality. All client-specified constraints were met successfully through our system. So again, this has been our final feedback control system presentation by Colin, Hovden, and Trevor Reed, and thank you very much.